No, I don't think the mic was on. Oh, it's on. Great. So let's get started. Previously, I was demonstrating the first project. I think I did until after I have finished data partition. Is that? Did I do anything after data partition? Can anybody remind me? Chi-square. Yeah, that's I believe that's in Stat Explore. Yeah, I think so. And after Stat Explore, I did some is that cherry replacement? I replaced some values of a couple variables with missing. I think that's the deal. And there are two tasks or two techniques that are in the tutorial, but I didn't demo, right? Can you remind me what are those? If you have already gone through them, that would be perfect. Then you know what I'm talking about. I think that's the 6th chapter of that. Do you have it? Do you have the tutorial?
You sent it over to chapter 6.
Yeah. Did anybody get a chance to go to follow the tutorial and did it yourself? Yeah. Sedanshu, what are those topics? I remember one is transform variables. What's the other? Regression? I think regression is the other chapter, but the same chapter with the transform variables. What is the third section? Replacement? Well, the binning. Oh, that might be it. The binning. Yeah. Right. Oh, so binning and what's the other? Log transformation. Both of them are in transform variables. Yeah, it's coming to me. Great. So the point of I want to mention homework 1. Yeah, homework 1 has some hands-on problems, right? It asks you to do 3 things. One is to find the missing, to report the extent of missing values. What tool would you use? What node would you use to do that problem? Stat Explore. Exactly. Yeah. Stat Explore. It's the second node that we did here. In the results window, it will give you an overview of the number of missing values in each of the variables. And the variables being separated into 2 types. One is class variable, the other is interval variables. Great. The second question was asking you whether or not you can find any problem with area codes and states. Right. In terms of identifying or discovering variables that are abnormal or values that are abnormal, the best tool that you have or best mentality that you have is using visualization tools, using exploratory graphing techniques. But there are different tools available and appropriate for different kinds of variables, right? If you remember, let me see. Let me bring up the slides. Control. Wait, hold on. So tools like this, histogram, would be best for trying to discover if there's any outliers in interval type of variable, you can simply make a histogram and then see if there are any bars that are lying away from the group of values, and you can quickly identify. Using scatter plot, can even find relationships between abnormal values across two different variables. But that same technique, at least it can help you identify abnormal values the same way, or will reach the same conclusion as if you were using the histogram, right? But this view will give you 2 dimensions of the data. So things like that. But these are these are interval variables. What about categorical variables? What kind of graph do you have available to you? Right? Can you think of any?
Pie graph?
Pie graph. Definitely, yeah. Pie graph will show you the proportion of observations in each category, and you can rank the categories arbitrarily or according to some kind of alphabetic order, right? Definitely. There are other tools similar to pie chart, but give you a different flavor or a different perspective of the data. It's a bar chart, basically. Bar chart, lie them horizontally or vertically. The idea is the same. You can get a sort of the big picture of how much each level is represented. So, in order to identify if there's any problem with the area codes and state variable, both of them are class variables, you would make graphs, either kinds or both, either by pie chart or bar chart or both, and look at each value specifically. And the kind of problem you may discover will be something like that we kind of touched on previously. I think it's missing. Here it's a table, but imagine that you make a bar chart or pie chart about the different brand countries, the origin of the automobile manufacturer. If you imagine a pie chart, and you have a piece with USA, you have a piece with France, you have a piece with US, and a piece with Europe and possibly others, and the piece about USA and France will be tiny. The piece with the others will be major, bigger pieces. And so you can immediately, kind of sense some concern. There's some data in the data set that is very, less represented. And when you look at the label and all the labels and you examine them, then you start to see overlaps. But for categorical variable, by design, it should be mutually exclusive labels. So that's the way you would look for possible errors. That's one scenario. But also, imagine that you're doing a pie chart with the U.S. states. And let's say, and you found 13 states, as if there are 13 pieces of the pie in the graph. What would you think? And what would you do? I would look at the 13 labels to see if there are states of the U.S. as the data set was supposed to represent, and I'll think about if 13 states is a good number here. Should there be 50 states? Should there be fewer than 13 states, or why 13? That's my question, right? So that is another approach, but using the same technique. So I would suggest you use the same technique to approach that question. And it's something else I'm going to talk about a little bit later when I demonstrate SAS that is kind of related to this question as well. The third question is asking you to transform. Yeah, great. So that will bring us to here. So I'm going to do a transform variable demonstration here following the replacement. It should be in the modify somewhere here. Transform variables. Okay, so is that mine? No? Wait. So in the tutorial, transform variable node was used for two purposes. One is to log transform some of the variables. Another utility is to, what did it do? Binning, the binning part. Binning is slightly more complex. I'm going to talk about, hopefully, if I had a chance, I would talk about later. For log transformation, the purpose is basically to make the distribution of a variable more normalized, right? Is to increase the normality of the variable by not fundamentally changing the information that's represented by the variable. And why do we need more normal distribution? Because some of the models, including regression, its performance depends on how far away the distribution is from normal. If it's highly normal, the performance is expected to be optimal for regression. If the distribution is highly skewed, highly different from normal, there may be some problems with the predictions. Okay, so let me go specifically into transform. There is a when I highlight the transform variable, there's a tool very neat. Go to the formula. You can construct a custom formula to specifically transform these variables or selected variables in a way that you want, like +1, +2, +3. You can construct a formula. But the reason I'm using this is not for customizing the formula for now. The reason I'm using transform variable, I'm using the formula tool here, is to quickly get a sense of the distribution of the variables without generating different graphs. So here you'll get a list of all the variables, all the input variables here in the data set. When you scroll through the different input variables, either a histogram or a bar chart is created for you at the upper portion, and it's so quick that it's almost instant reaction. So and when I want to examine the distribution of the variables, this is the quickest tool I can go, the most efficient place of the software I can go for a quick visual examination of the different variables. So let's look at some of the variables. I would suspect that the donor age variable to be fairly normally distributed. It's okay. It's not very normal, but it's not very skewed as well. it does have a heavy representation by senior people here, people aged above 60. It's a large proportion of senior people. But then if I link that to the purpose of the project, then I would probably understand. Because more senior people tend to have more money to donate because they don't have kids to raise. And they tend to be more generous, hopefully. So it works somewhat favorably to the project. But if I look at another variable, lifetime gift count, how do you think that the distribution will be? Is it going to be close to normal? Is it going to be symmetric? If it's skewed, in which direction do you think it will be skewed? Where's the tail? Left skew?
Left skew.
So the tail will be extending toward left. So those who have fewer count of gifts will have less representation in the data set. And then those with the larger value for gift count will have higher representation in the data set. Does that make sense? So that means the bars for larger values will be higher. The bars for fewer values, for smaller values, will be lower. That's left skew. Does that make sense? You have more people who are donating a lot of times. You have less people donating a few times. Does that make sense?
Well, we used to compare the mean and the median to decide which way that.
That's right. That technically, yes.
Then
Technically, that's how skewness is defined. You compare the mean and median. But visually, you can get a quick sense. It's where the tail is pointing to. So let's take a look. Gift count. Is the tail pointing left? It's pointing right. So that's somewhat, it's opposite from the story that was narrated earlier. It's those who donate a lot have a lower bar. It's those who donate very few times or even none have higher bars. The bars represent the percentage of the data set. The bar is representing the frequency, right, of that value. So things like that, it's understandably right skewed because fewer people would be willing and able to donate. More people would be, willing to donate fewer or try to avoid donating if desirable, right? So this is a typical case of a right skew. You can think of many, many scenarios where a variable is right skewed. Income, right? Wealth, income, the same thing. I don't know. What else? Number of children. Definitely, yeah, definitely. Yeah. Although you can also expect a small tail on the left, but the right tail will be much longer. Just because there is a cutoff here, it's not going to be possible to give birth to -1 children. It's only possible to give birth to 0 and zero fertility. But it's still possible to give birth to 20 kids in a lifetime, right? But those would be rare cases. So that's why it's right skewed. Here, it seems that the vast majority of people has given 1 time because the bar is highest, close to 1. That may give you that impression. Question?
What does your x-axis represent?
The gift count. Number of times that the person have given.
Throughout the whole lifetime.
Yeah,
Okay.
yeah, yeah. Or as much as the data can collect.
Okay.
Yeah.
So more people will donate in that specific area.
Yeah, yeah. So the larger percentage of people have donated between 1 and 9.8 times overall. So this might have given you the impression that the majority of the people in the data set has given one time or once, right? Does it?
It shouldn't, because it's not showing that many people haven't donated or never donated. Maybe.
That's right. Yeah. Yeah. It seems everybody has donated at least once in this data set, which also makes sense. If the company only targets those who have donated, then it may make sense to them in terms of increasing the chance of getting donations. So, but we can extend beyond the scope of these exercises to talk about those. But I would defer talking about those for now. But the point is that you can get a quick glance of the distributions by using this tool, very fast. And later on, I'll demonstrate another alternative to generate these same kind of graph, but it'll be much more time consuming. Although it gives you more control, it's more time consuming. Okay, so while we stay in the transform variable node, we will do some specific transformation here. Under training for variables, let's go into it. And while the tutorial talked about log transformation is to fix the distributions. So for variables like gift amount count, or everything related to average gift, everything related to the gifting histories, you would necessarily find the distribution to be skewed. So you want to take a log transformation on these variables, as the PDF tutorial have demonstrated. The quickest way is to select everything that you want to apply the same kind of transformation, and then you just click one of these for the method and choose the right method that you want to apply. And then it will apply to everything that's selected, right? So, but however, if you want to apply another transformation, such as such as this, then you will do the same thing here, and then select whatever method you want to apply for transformation, and then confirm. Confirm by OK, and then make sure you run the node. Yeah. After it's successful, it's always good practice to check it, to make sure nothing unintended has been done, and everything has been done as the way it's intended to. For these results, it gives you a summary of what has been done here. So for these variables, they are treated as input, as the original values, and some operation has been applied to them, like log transformation. So the new variables are computed and included in the output data set that's coming out of that node, right? It has a new name. It has a prefix of the type of operation that you have applied. For instance, these log indicates that I have applied log transformation to these variables. SD or STD means I have applied standardization to this variable. And same thing here. It just gives you textual feedback. But it would be nicer to generate some distribution plots to make sure that, if it's a log transformation, then the distribution has become more normal, to compare what was before and what was after the transformation, to sort of give a visual demonstration that you have done it and it's correct. So in that sense, I will then use the exploratory graph tool. I could also drag another transform variable here to connect to that and to generate those graphs for those that have been transformed. Does that make sense? Right? But doing that twice, it's kind of, I don't know, you can do that definitely for the homework, but it's going to be the same technique. I'm not going to demonstrate it, to save some time. I'll use an alternative here. So this is a process model of data mining. And imagine that there is a data set that is being passed through this stream. And there's a data set accepted as input and feed into the first node for analysis. And something was done probably and applied to the data set, and it's passed through to the next node. So this kind of a morphing data set is passed through. And by the end of it, you have an output data set that is, that has changed because of all the operations that you have done. How to get those data set? After highlight the node, you can go to exported data. That is where you can extract the exporting data set. And you can do some exploration on these. So this is what I'm going to do. The mission here is I want to generate some distribution graph about those variables that have been transformed. One is log transformation, the other is standardization. By looking at their distribution after transformation, I should see a difference, right? So in the exported data set, I have two data sets. As you can imagine, I have already done data partition. So all the transformation have been done, applied to both of the sets. I can choose one of these. After highlighting that, I can do explore. And so this explore tool is ubiquitous. You can find it everywhere here in SAS EM. I just haven't pointed it out to you yet. This is one place you can do it. But keep in mind, try to remember, every time you use explore, try to remember to change some setting here. Unless your data set is immense, like 100 million, that would be immense. 100 million records, that's immense. That takes a lot of memory, and takes some time even for SAS to process, and that won't be worth it. And since the data set is large, you can take a random sample of that big data set to do exploration. But here, for this course, most of our data set is not immense. So make sure you get the full data set to explore rather than a sample, right? So something to remember is whenever you're going to explore, you make sure you change the default to max. Default is saying it's taken a sample. It's taken a small sample of the entire data set. But using max is trying to use the entire data set and apply. And that's done. So you can see that the fetch rows has become has changed from 2,000 to 9,000. Now you're using the full data set to do explorations, and that gives you the most accurate exploration results, right? Now you're ready to generate some graph. It's in actions plot. And then you have a whole range of tools here. You have different graphs to make. Let's quickly make something. So I want to look at the distribution of the continuous variable. So what graph should I use? Line graph. What is line graph? So line graph is more like scatter plot linked together by lines. They have two dimensions. You have x and y, right? Does it give you the distribution, or does it really give you the correlation between two variables? It's rather those bars. But for continuous variables, we call them, by convention, we call them histogram. They look like bar graph, but they're histogram because the bars are sorted. As with bar chart, the sorting can be arbitrary, right? But histogram has the bars sorted. So we want to use histogram. The default type is OK. We go to next. We choose the variable to do. Question? Oh, okay. The sample, right? So right after you go into explore, you would change default into max, and then you hit apply. This number will change. Yeah, great. And so actions plot again, histogram, next, and so choose the variable. Can you tell me which variable I did log transformation, and pick one? Lifetime count, and it'll be obvious here because it has a log here, right? It has a log, and since previously I looked at GIF count, so I look at the GIF count. If you remember the x-axis previously, it's between 1 and 80, maybe something like that. Lifetime, change the row to be x. And for histogram, there's only one variable needed. And on the y-axis, you can choose to display frequency or percentage. You know, slightly different versions, but give you the same shape. I'll do the percentage for now. This one is modifying the name. It's not necessary. Or setting some conditions to filter the rows. And we don't want to do that. And give some customized title. Footage, none. X is log. Count. Gift. As long as it makes sense. Y is percentage, or the percentage, and we can toggle X's on both sides. So that's it. This is the distribution of. So what do you notice? Is the distribution the same, similar, or very different? Do you see a long tail? The long tail is gone. Yeah. And what else?
The ranges are reduced.
The ranges have changes. The minimum now is 0.69. Yeah. And the maximum is 4.5. Something close. So it is a dramatic change, right? Can you imagine what the log transformation is doing? Kevin?
No.
Han?
It's normalizing the width.
It does. Yeah, it's eliminating the long tail in a large part. right? Kevin?
No, I was just gonna ask it, is initially usable because we can only have integers of how many times gifts were given, so
It's a good point, yeah. So the values are now not making much sense for gift count. It makes a lot of sense, yeah. So this change to the variable, it does have plus and minus signs. It does correct the distribution. Is everybody clear on, first of all, technically, is everybody clear on why it's correcting the you know, the what? Skewness of the distribution? It's okay to say no, because then I will demonstrate. If everybody's clear, that there's no need for me to demonstrate.
Please demonstrate.
Okay, perfect. So, hopefully this works. It will help if, you know, if we review a little bit of a background of what does log transformation do. So, even if I use log instead of log 10, it's the same logic, right? Log 10 of 1 equal 0. Correct me if I'm wrong. Log 10 of 10 is 1. Right?
yes.
Yeah. And log 10 is not defined. Right? Anything equals 0 or below 0 will be undefined. So this is the original variable, and this will be the log version of the variable, right? So what was a 1 becomes 0, but what was 100 becomes 2. So you can imagine that if the original variable has this kind of distribution in terms of histogram, then if this is 100, then after log transformation it becomes 2, right? Very, very small, and this is 0. And what was 10 become 1, right? So after transformation, it will kind of become this. So that's why the tail is gone. It's the sparse regions are pushed toward those lower values, and then everything is pushed, squeezed into this distribution that looks more normal. Yeah. So that's why, technically. But the problem is it's making the values nonsense in terms of what the variable is supposed to capture, right? It's supposed to capture the total lifetime count of gift. So then the question really is the value to do that, right? What problem might be might it create if we do that? Sorry, I can't record that. So when you hear the recording, this is gonna fade away, just because I'm far away from the mic. But there's no other solution for now to that. This is one. This is what a log transformation is doing. So this x-axis, you can imagine it to be original variable, and the y is the log version of the variable. If it's 1, then after log transformation becomes 0. If it's 10, it becomes 1. So that's a correspondence. it does change the value of that, but it didn't change the comparison evaluation of the relative, not relative, of the arbitrary comparison of two values. So if we have two values, this is out of scale, but pretending that this is 100, after log transformation becomes 2, these two values, 100 is bigger than 10. After log transformation, it's still bigger than 10, although it's not bigger by that much of a scale. I can't say for sure what is the term in mathematics. Can somebody remind me? But this is the, monotonic correspondence between the original and the converted variable. And it is fine to do that here because we can always convert back. So it makes the case that we can do that. Does that make sense? Kevin?
Professor, sorry, the default, we'll call it log function here, is it?
It's a natural log,
or is it
yes.
natural log?
It's a natural log. Yeah.
So then is it just, I guess, is it just changing the bins or the classification? Because then I guess you can change that back. Like I did e to the 0.69.
It's 0.1, 0.3 something like that. 0.5?
According to this calculator, e to the 0.69 is rounded up to 2. It's like 1.99. So I guess it's saying that.
It's 2. Okay, right.
Start at 2, and they end at.
That makes sense.
E to the 1 would be maybe like 3. So from 2 to 3.
Yeah, that makes sense.
10%, and then it. So I was just asking.
And we can can we generate that?
I don't know if you can switch it back to see what the actual energy count is.
Yeah, the original variable is rejected by now because it's being transformed. So the original variable is hiding from this node. So to directly compare them, it takes a little bit of time to prepare. But you're right. By conversion, the minimal value of that variable is 2. Yeah.
Okay.
Yeah. So for models like regression, it benefits from converting the highly skewed variables to become more symmetric. Okay. I need to bring that the other table here. There we go. Okay. Now, so this is for log transformation. Another thing I did is standardization, right? So for standardization, I skipped some of the slides last time. Or I didn't skip, I didn't get to it, essentially. So let's review it quickly. That's a binning. Transforming. No. Right. So this is about normality of distribution and how log transformation can correct the skewness. So these are about the theory side. Where is the standardization? 31. Thank you. Great. So, z-score standardization. Essentially, what it does is to convert any distribution into one that has mean 0 and standard deviation of 1. So in a way, it kind of squeeze and remold any distribution into someone that is somewhat comparable to each other. So every 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 variable after standard deviation, z-score, standardization has the same mean 0 and standard deviation of 1. So that you can see, in that scale, how they are distributed specifically. It helps with neural networks a lot. It doesn't help much for most of the other variables. So regression doesn't need standardization, although the interpretation of the results may benefit from standardization, right? So for any distribution that may have a mean 10 or mean 100 and standard deviation of 8, after standardization, it will have a mean 0. So it's kind of centered around 0. And the spread is kind of readjusted to have a standardized spread. So I did a standardization on age, right? Age has a spread of between 18 to 80 something. So after I standardize a variable, it should have a mean 0, roughly, and a spread, a range of between -4 to +4, something like that. So I should expect to see that when I do a graph. Right, so I'll do another graph, same histogram, but this time on the H variable with the standardized stdh. Oh, by the way, I do see the original variable here. I do see the donor age. So later on, I can do the distribution of the other. So for donor age, select X. I will use frequency this time, but you'll see the difference. Histogram of standardized age. Standardized age. Y-axis is the frequency. So this is the distribution of age after standardization. The shape of it didn't change. It still has a high bars and higher values of age, although the values are now not in the scale that we come to understand age. It's between -3.5 to +1.6. It may give you the impression that it's not symmetric. It is not symmetric, but because of the skewness there, so the median here is not 0, but the mean is still 0. It's for sure, by definition, standardization will make the mean 0, and because of skewness, the median is not necessarily 0, so it doesn't overlap with the mean. That means there are skewness. So by providing this graph, you can demonstrate that I have done standardization correctly on this variable, right? And the good thing is that we have the old variables. So I'll bring that up. I'll do this first. I'll do the histogram of the original variable for gift count. So y'all can do your own way, or you can follow me. Maybe you're faster than me, which will be fantastic. Lifetime gift count. Yep. So I'll do the same thing as percentage as before. And now I'll skip the other things, but I'll do the X. This is gift count original. If we compare side by side the two graphs, the one on the right is the original gift count. The one on the left is the logged gift count. It's dramatic difference in terms of distributions, skewness particularly, as well as the range of it, right? but the two carry same information, not exactly the same, but after conversion it's the same, right? And something neat about SAS is that these graphs in the same view, in the same node view is linked. So their IDs in the back end are linked together. If I choose a point in this graph, it's going to be highlighted in the other graphs automatically. And because I said the log transformation is monotonic conversion, right? So if I select those lower range of values here, which part of those bars do you think will be highlighted? Will be selected, highlighted, because they're linked. Same lower ranges, right? Maybe not all of them, because by doing the log transformation, some of these values are kind of diluted into the other bars. So this is what happens. That's what I'm saying. Every data point that's included in this bar, or this takes this percentage of this bar. But if I highlight the other bar, it's going to be highlighting multiple bars on the left side. But you can see the correspondence, right? These are the exact linkages between the points. But only happens in the same node. In the same node. Okay, that's all I want to demonstrate for homework 1 as well as beyond. Any other questions before we move on? Good. Great. Okay. Now, these graphs are not saved. It's not even possible to save them. So once I close this window, it's gone. So just to make sure you know that. That's it. Okay. So let me briefly talk about the business world, what's happening, and we'll take a break. And we'll come back after the break. We'll do the case. Okay. This data science, data analytics, data machine learning, artificial intelligence. How do you think about that? How do you think about the whole movement of machine learning? I just want to know about your perspective. That's it. So I realize that people have different views, even on the same subject, even if probably have the same exposure to different information, but people have different views. I just want people to share these views. So feel free to talk and let me know. Let other people know. Kevin?
I mean, this is one thing that maybe I've heard. I don't know how true it is, how it isn't true. I don't know if there's a tendency to pick the lowest hanging fruits and say, all right, well, machine learning, has been